Well, first of all, thank you to the organisers for arranging what's been a wonderful conference so far, and I'm sure it will continue in that way. So today I'm going to be speaking about some joint work with Dylan McDermott, and the sort of goal for this sort of ongoing research project is to show how, by looking at classical theorems about monads, using the technology of relative monads, we can gain new insights and generalize existing theorems using this new conceptual understanding. So I'm going to explain what a relative monad is later on in the talk, but first of all I'm going to start off by giving some context for the problem we're considering. So we're going to start off with a question, which is this: what is the relationship between algebras and free algebras? And here by algebras I really mean the algebras for a monad. So, a very classical category theory fact is that there are two canonical categories associated to every monad. There's the category of free algebras, or the Kleisli category, and the category of all algebras. Now, given the category of all algebras, we can form the category of free algebras. And this is intuitive because every free algebra is a specific kind of algebra. But a bit more abstractly, we can construct it categorically as follows. So we're going to look at we can look at the free functor from the base category into the category of algebras. And now we're going to factorize the free functor into an identity on objects functor followed by a fully faithful functor. So we can always form this factorization for any functor, and in this case it gives us the category of free algebras. Now going the other direction is a bit trickier, but we can still ask the question: if we're given a category of free algebras, can we reconstruct the category of all algebras? And perhaps, well, somewhat surprisingly, it turns out that we can do so. And this is an old result of Linton, but it's perhaps not as well known as it ought to be. So what I'm doing here is I'm taking some monad T on the category E, then I'm looking at the Kleisli category, or the category of free algebras, and taking pre-sheaves on it. So looking at the contravariant functors intersect. Now here KT is the inclusion into the Kleisli category, so this functor is re-indexing the pre-sheaves along the inclusion into the Kleisli category. Now we can look at the Unedra embedding of E into the category of pre-sheaves, and now we have cospan, and we can take its pullback, and it turns out that this pullback is precisely the category of algebras for the monad. So this allows us to construct the category of algebras from the category of free algebras. And intuitively, this is capturing the fact that the category of algebras is some sort of co-completion of the category of free algebras. So I'm going to call this characterization of the category of algebras the pullback theorem for monads. And just to note that during the rest of the talk, just to save space, I'm going to use this hat notation for the category of pre-sheaves. Okay, so now we know we can go back and forth, we can construct the category of free algebras from the category of algebras and the category of algebras from the category of free algebras. However, it turns out this isn't the whole story. In fact, in many cases, for many classes of monads, we can actually sharpen this characterization of all the algebras in terms of some subcategory of the free algebras. And so what we're going to do is, instead of pulling back some Kleisli category along a Unedra embedding, we're going to pull back some sort of Kleisli category along a nerve functor. So what do I mean by a nerve functor? Well, if we have any functor, so here a functor from A to E, we can form a new functor which goes from E into the category of pre-sheaves on A. How is this defined? Well, it looks like the Unedra embedding, except we restrict along the functor J here in the contravariant argument. So we can always do this as long as A is suitably small, or J is suitably small. And in particular, when we take J to the identity functor, we just recover the usual Unedra embedding. So now I'm going to give a sort of theorem schema for what I mean by nerve theorems for monads, and then I'm going to give some examples. So a nerve theorem for a class of monads in general is going to look something like this. We're going to take some class of monads, which we call nice, and so the meaning of nice is going to depend on the precise theorem statement. then the theorem in question will say something like there exists some subcategory of E, the category in which we're taking the monad, such that if we restrict the quasi-category of the monad to the subcategory, then we can look at the pullback. So now we've got this restricted quasi-category, restricted to this subcategory A. We can re-index the pre-sheaves along the inclusion of A into this restricted quasi-category. And now instead of pulling back along the Unada embedding, we're going to pull back along this nerve functor. And so a nerve theorem in general is going to say that this diagram forms a pullback. So the category of algebras can be described as a pullback over a nerve functor. And so in particular, Linton's theorem about pullbacks is a particular case of a nerve theorem where we take the subcategory to just be the entire category. So we take J to be identity. And this is not such an interesting nerve theorem because usually we want to take A to be as small as possible. So let me give a couple of examples. So first of all, we can take a finitary monad on the category of sets, so a monad preserving either filtered colimits or sifted colimits. And then we're going to take the full subcategory of the category of sets on the finite ordinals. So abstractly, this is the free co-completion under finite coproducts. Now we can look at what this restricted quasi-category looks like. So it will turn out that this embedding of the category of finite ordinals into the restricted quasi-category is precisely the finitary algebraic theory associated to the monad. And furthermore, there is a nerve theorem that I'm not going to explain right now, but it exists and says that if we look at the pullback from the previous slides, in this case, we get that the category of algebras for the monad forms this pullback. Now, why is this interesting? Well, it's also fairly easy to calculate that this pullback, or the pullback of this cospan, is given by the finite product preserving pre-sheaves from this restricted quasi-category into the category of sets. And I said that this restricted quasi-category was essentially the algebraic theory associated to T. So this tells us that the category of models for the finitary algebraic theory associated to T coincides with the category of algebras for the monad. So this is part of a proof of the monad theory correspondence, the classical monad theory correspondence. Now here's another example of slightly different nature. So we're going to take T, our monad, to be the free category monad on the category of graphs, and we're going to take delta naught to be the full subcategory of the graphs on the linear graphs. So by linear, I mean that we have some sequence of vertices and just a single edge from one vertex to the consecutive vertex. Now we can look at the restricted Kleisky category for this monad, and it turns out to be precisely the simplex category. And there is a nerve theorem that says that the pullback of the shape in the general theorem schema holds and exhibits the category of algebras for this monad, which is the free category monad, so the algebra is exactly the small categories, as this pullback. Now why is this interesting? Well, it tells us that small categories can be expressed as certain simplicial sets satisfying this pullback condition. And it turns out that this pullback condition exactly corresponds to the Segal conditions for categories in terms of simplicial sets. And there are similar characterizations for other kinds of category-like structures, so for instance, strict omega categories. Okay, so now I'm going to get on to what I mean by particular nerve theorems. I gave you a shape of a nerve theorem, but what are the actual instances of nerve theorems? So it turns out there have been a lot of different frameworks in which various results, which could be called nerve theorems, have been established. So I'm not going to go into any details for any of these frameworks, I'm just going to mention them, and if you've come across them before, then you'll recognize them, but if not, you can see they've been studied quite a lot. So as far as I'm aware, the first sort of study of these nerve theorems was due to Tom Leinster in his work on familiarly representable monads. Then we have monads with arities, which were introduced by Weber. There are several nerve theorems for monads preserving some class of colimits. And then we have the nervous monads of Burke and Garner, and then this work was continued. by Lucian, Wright and Parker. Okay, however, there's some shortcoming with these various results in that, well, a conceptual shortcoming rather than a technical shortcoming, in that we have all of these different frameworks in which nerve theorems have been established, but none of these general nerve theorems completely subsumes the others. And so there are examples of nerve theorems that fit into one framework which don't fit into the other, and so on. And furthermore, there are examples of nerve theorems which aren't captured by any of these frameworks. So we're naturally led to ask, is there some sort of general phenomenon which includes all of these nerve theorems? And, well, the answer I'll give during the talk is that yes, and I think this is one of the questions that the theory of relative monads clarifies. So what I'm going to do in the next part of the talk is show that these nerve theorems arise as a consequence of two more fundamental facts. So this brings us on to relative monads, which are the sort of key player in the talk. So let me tell you what a relative monad is. So conceptually, a relative monad is a generalization of a monad where we relax the requirement that the underlying functor of the monad be an endofunctor. How do we do this? Well, we need some functor that will act as a sort of identity functor to express the unit. So what we're going to do is we're going to fix some functor j, here from A to E, which we call the root. Now we can take an arbitrary functor with the same domain and codomain for the underlying functor of our relative monad. We have a unit, just as in an ordinary monad, but now it has to go from j to t, rather than the identity to t. Now the part of the definition that looks most different from the usual definition of a monad is this part. So we can no longer naively express the multiplication operation because we can't iterate this functor t because it has a domain different from its codomain. So instead we reformulate the definition in terms of an extension operator. So the extension operator says that if we have some morphism from j of x to t of y, we can extend it to a morphism from t of x to t of y. So this is encoding some sort of freeness property. So I should say that relative monads were introduced by Altenkirk, Chapman and Oosterloo about a bit over 10 years ago, so this is a known definition. And in particular, when we take j to be identity functor, this is equivalent to the usual definition of a monad. You just have to do a bit of moving things around to see this. Now, one thing I'm not going to do is give you any examples right now, because we're going to see that actually the relative monads we're interested in during this talk are going to be a very special kind. So first I want to mention that just as we have the two canonical categories associated with every ordinary monad, we have two canonical categories associated with every relative monad. So we have a category of free algebras. How is this defined? Well, we take our relative monad T. The objects of the category of free algebras are defined to be the objects of the domain category. And the clysomorphisms from x to y are going to be the morphisms from j of x to t of y in the codomain. So this very much looks like the usual definition of a clysi category for a monad, and it works in essentially exactly the same way. So you have an inclusion functor into the clysi category. We also have a category of algebras, and this looks a little bit different in the same way that a relative monad looks a little bit different from an ordinary monad. So we have a definition of a T algebra, which comprises an object in the codomain, so just like an ordinary monad. And now, again, instead of having an action of the algebra, we have to have this extension operator. So this says that given a morphism from j of x to e, the underlying object, we have a morphism from t of x to e. And again, this is encoding some sort of freeness property. Now, these T algebras compile into a category of T algebras, so with morphisms just preserving the structure in the sort of evident way. And we have a forgetful functor from the category of algebras into the codomain of the relative monad. Now, I'm still not yet going to give you some examples, but I will do very soon. But first of all, I'm going to mention that essentially the key step in understanding these nerve theorems a bit more conceptually is to study the question we looked at right at the start, which is what is the relationship between algebras and free algebras? So I didn't mention it, but we can construct the category of free algebras from the category of all algebras by taking the identity objects fully faithful factorization, like for ordinary monads. And we have a corresponding generalization of Linton's pullback theorem for relative monads. What does this look like? Well, we're going to fix some functor from A to E, which we require to be dense, and I'll come back to this assumption in a moment. And we're going to fix some J relative monad T. Then, as a generalization of Linton's result, we're going to look at the precies on the Kleisy category for the relative monad, and we're going to reindex along the Kleisy inclusion. And now we're going to pull back along the nerve of J. And the theorem states that this category of T algebras forms a pullback square like this. And so in particular, when we take J to the identity functor, this recovers Linton's pullback theorem. I'm just going to mention as a sort of offhand remark that I won't go into any more detail with here, that this implies that the inclusion of the free algebras into the category of all algebras is dense. And this is a very useful fact. And again, it sort of expresses the intuition that the category of algebras can be formed as a sort of co-completion of the category of free algebras, which is a somewhat surprising fact for relative monads. Okay, so you can probably see that this pullback square looks very similar to some pullback squares we saw earlier. So what is the relationship? So now I'm going to introduce the class of examples of relative monads for this talk. So I will mention there are many examples of relative monads that aren't of this shape, but we're going to be interested in a certain class here. So there's one very easy way to build examples of relative monads. So we can start with a monad on some category, E. Then we look at any functor going into E, and we can precompose all of the structure of the monad by this functor, and this gives us a J relative monad, which I'm going to call J composed T. Now, after having done this, a natural question to ask is, what is the relationship between the free algebras for the original monad T and the free algebras for the relative monad, and also what's the relationship between the algebras for the monad and relative monad? So there's a very easy way to characterize the free algebras for the relative monad. How do we do this? Well, we're going to look at our functor J, which is part of the data for the precomposition. And then we're going to look at the Kleisy inclusion for the monad T. And then we're going to do something we did earlier, which is take an identity objects fully faithful factorization. And so it turns out that the identity objects functor is precisely the Kleisy inclusion for the restricted relative monad from our original monad. And so in particular, when J exhibits a full subcategory, so when this is a fully faithful functor, the Kleisy category for this relative monad is precisely the restricted Kleisy category that we saw before in the nerve theorems. What about the relationship between the algebras in general? Well, in general, we can't characterize the algebras for the relative monad in terms of the algebras of the monad. However, we always do have this comparison functor from the category of algebras of the monad into the category of algebras of the induced relative monad. And so we come to the most important definition of the talk, which is this. When we have some monad on a category E and a functor into E, then we say that the monad is J if this comparison functor is an equivalence. So if the category of algebras for the induced relative monad is equivalent to the category of algebras for the monad we started with. So this is not always true, and it will be interesting when it is. And so we have a very nice characterization of the J monads. So in fact, a monad on E is J precisely when this forgetful functor from the category of algebras for the relative monad has a left adjoint. So it always has a J relative left adjoint, but it won't necessarily have a left adjoint. But when it does, the monad T is J. Now we have everything we need to build up the picture of what nerve theorems mean in the context of relative monads. So we can reformulate the previous slide and the pullback theorem for relative monads into a nerve theorem for J monads. So again, we're going to fix some dense functor J, and we're going to let T be a monad on the codomain of J. And then we have the following statement that the category of algebras for the monad forms a pullback along the nerve of J, and taking the pullback along the Kleisby inclusion for the relative monads, if and only if T is J-ary. So it's a very strong characterization. It exactly tells us when the category of algebras forms these kinds of pullbacks that appear in nerve theorems in terms of the induced relative monad. So in particular, all of the examples of nerve theorems that I mentioned earlier are captured by this framework. So all of the classes of monads that appear in these theorems are J-ary. And this essentially follows from this theorem here. Okay, so in the last few minutes, I want to briefly change topic a bit, because so far I've only been speaking about ordinary category theory, and maybe some of you attended my talk last year, and you'll know that I'm very interested in understanding things formally. So what do I mean by this? Well, we're interested in understanding at what level of generality this pullback theorem and nerve theorem hold. So I've just spoken about ordinary categories in this talk, but I just want to briefly mention that actually we work in a formal categorical setting, so we work in the context of exact virtual equipment. I'm not going to explain what this is, but it's a particularly nice kind of double category that allows us to make the arguments we need to make. And there are a lot of examples of exact virtual equipment. So for instance, ordinary categories, enriched categories, internal categories, and various kinds of generalized multi-categories form examples of exact virtual equipment. So this really applies to a lot of different examples. So for instance, we don't need any assumptions on our monoidal category V for enrichment for the nerve theorem to hold. So we don't need any sort of local presentability assumptions or anything like this. Yeah, so there's one more thing I want to say, which is that I haven't mentioned at all how one would go about proving the nerve theorem or the pullback theorem. And it's fairly easy. If I've given you the statement, you could go off and, with a bit of work, you could prove it yourself without much difficulty. It just relies on some currying, uncurrying, Yene dilemma, whatnot. But this isn't very conceptually illuminating. It's quite fiddly. And furthermore, when we start moving to the formal setting, it becomes much more complicated to describe. So we really would like a more abstract approach to proving this pullback theorem. And so in the last slide, I'm going to mention how we do this. So let me actually skip this part. So I'm not going to mention virtual equipment. Instead, I want to mention a slight reformulation of the pullback theorem that holds much more generally. So we're going to introduce a notion of limit in a double category called a semanticizer. And a semanticizer looks very much like a pullback, except it involves both functors and distributors, or profunctors. So given a diagram of this shape, which looks a bit like the shape for a pullback, except we've got a distributor along the bottom, a semanticizer is given by some category, along with a distributor projection and a functor projection. And then it's universal in the sense one would expect for a pullback, except now we're looking at the distributors into K and the functors into E. So it's universal such that this sort of diagram can be used. This is very much like a pullback, except involving both a distributor and a functor. And this makes sense in any virtual equipment.
Going in the right direction?
So yeah, this is going in the right direction, but it's in counterintuitive direction. So when this universal property involves taking the conjoint of K, which will flip the direction around. So we're making use of the fact that we can essentially re-index along functors. And you'll see this appear on the final slide. So we have the following theorem, which the pullback theorem for relative monads is a consequence of, that the category of algebras for a relative monad forms a semanticizer involving the Kleisby category for the relative monad, the Kleisby inclusion, and the conjoint of J. And so as a consequence, we can build semanticizers in any virtual double category with pullbacks and pre-sheaf objects. And in particular, then the pullback theorem I stated earlier follows from this general semanticizer theorem. So this is our actual proof technique, and I think that's where the interesting details of our paper are. but I'm out of time now, so let me summarize. So for any dense functor, we have this pullback theorem for a relative monad, which exhibits the category of algebras as a pullback along the nerve of the functor. Now, I didn't have time to mention why density is important or whether it can be removed, so if you're interested, you can ask me about it. And the nerve theorems that have appeared previously in the literature appear as special cases of this theorem. And finally, this theorem holds in a great deal of generality in any exact virtual equipment. So we have a preprint on arXiv, and if you find any of this interesting, even if you never encountered these concepts before, if anything caught your eye, please do come and talk to me, and I'll be very interested to talk to you. Thank you.
Thanks very much. Let me start with a silly question. Why do you call this a monadizer?
It's a good question. So there's a whole aspect of this story I've not had time to talk about here, which is the relationship between relative monads and the structure-semantic adjunction from the Veers and Linton's work. And so it turns out that semanticizers in more general context are a crucial aspect of the structure-semantic adjunction. And so it comes from this link to those.
Okay, so, yeah.
Thanks for the very nice talk here. It looks in the ending sequence here that J didn't really need to be a functor, it could have been a profunctor or distributor.
Yes.
How much goes through if you relax it to that situation?
Yeah, that's a good question, thanks. So actually, everything goes through if you replace J with a distributor. And essentially the reason we didn't do it like that is because we thought there's already a lot of complexity in working with all these new definitions, and so it would be simpler to use the existing definition of relative monad. But actually, the fact that J is a functor is not used anywhere in the proof. Thank you.
Any more questions? Okay, well, if not, then let's thank Nathanael Arkor speaking.